Okay, I think we're ready to start now. Thank you all very much for coming. Thank you to our speakers. This is one of those interactive press conferences where there's more time for questions. And Nick Arndt, who is a EGU division president, will take care of the introductions for me. So I'll pass on the word to him. And the press conferences are on how critical are strategic mineral resources.
Okay, thank you. Thank you, Barbara. Now, my name is Nick Arndt. I'm a professor of geology at the University of Grenoble in France. And I'll share this meeting. The way I'm going to do it is start with a small, brief introduction. Then I'll introduce the panel members, and they will talk for a short time. I will ask for questions after each presentation, and then we can have a more general discussion. I wanted to start by saying that Europe spends roughly 50 billion euros a year for the Common Agricultural Policy. This is a policy designed to make sure that Europe is never dependent in the future on imports of food. Europe spends virtually nothing, until recently has spent virtually nothing to assure a metals policy. Yet Europe is dependent, European industry is dependent for about 97% or 100% on importations of metals. In the 70s and 80s, this was not a problem because metals were available on the general market and the car manufacturers could simply buy what they wanted. But they received a shock 3 years ago when China, which is the major producer of rare earths, started to restrict supplies. What this has caused is a general awakening at different levels in the European Union and in the member states of the fact that Europe requires metals. European industry, European society requires metals, and these metals are produced almost entirely outside of Europe. So this is the subject of our discussion of this panel conference, and the three speakers will address different aspects of the subject. Now, to my left is Olivier Vidal. Olivier Vidal is a scientist, a researcher at the same university as me, at ISTER, University of Grenoble in France. He will also tell you the other things he's involved with. Next is Friedrich Wellmer, who is currently chair of a section on management of natural resources at Le Studium in Orléans. It's a think tank in Orléans. And he's the retired president of the German Geological Survey. And then at the far left is Richard Harrington, a professor of the Department of Mineralogy at the Natural History Museum in London. Okay, now I'll pass the word to Olivier. You're going to start. Olivier will be the first person to talk.
Yeah, good afternoon. My name is Olivier Vidal, as Nick said, so I'm a geologist, a mineralogist, mostly interested by the thermodynamic modeling of geological processes and, for instance, the fluid rock interactions, which can be responsible for the formation of ore deposits. I'm also coordinator of a new ERAnet, which is called ERAMIN, on the industrial handling of raw materials. So this is a project which is supported by the 7th framework program. The main objective of ERAnet of ERAMIN is to set up networks and mechanisms in order to foster the research on raw materials and also the coordination of research at the European scale. Well, I think that's it for the moment, depending on the question you have, so I will certainly have the opportunity to develop on that.
Okay. I think we'll pass on directly to Richard. You'll talk now. Richard from the Natural History Museum in London.
Thanks very much, Nick, and thanks everybody for coming along. I'm based at the Natural History Museum, and I coordinate ore deposit research at the NHM, but I'm a university teaching at the university, the Royal School of Mines in London. My particular aspect here is I research into mineral deposits and where they occur, where they form in the Earth's crust. And a particular area that I wanted to highlight, and it sort of follows on from what Olivier was saying, is that Europe relies heavily on natural resources, whether we like it or not. And as Nick pointed out, we largely import those from outside of the European Union, and indigenous production of metals is quite small. Obviously, in the past, it's been easy to source things from other parts of the world, but as Nick pointed out again, it just takes political or economic crises to put the pressure on European industries, and we're seeing that quite a lot. And it's not just rare earth metals. And I really want to illustrate it with another important metal, which there are 14 metals or metal types that have been identified by the European Union as being critical to future industry in Europe. And these range from things like the rare earths to platinum group metals. And a metal I want to highlight is cobalt. And cobalt is one of those metals, you never really mine it on its own. It's always a metal that comes as a byproduct of other mining operations. But it's absolutely critical for a lot of industry, hardening of steels, particularly useful in new battery technology, renewable batteries, and superalloys, which obviously are used by aerospace industry. So, for Europe, these are pretty critical things. Now, there's a world production of 70,000 tons of this, of which Europe uses about a third. So more than 70,000 tons produced. Europe produces 27 tons of that metal indigenously. Now, it's interesting because there are mineral deposits around the world, very similar to ones that are currently mined in Europe, that have the potential for producing cobalt. But due to the use of technologies that may be inappropriate for modern society, that we're actually throwing that cobalt away. And just by simple implementation of new technologies, we could improve indigenous production of metals from existing mines, but also there's huge potential still in Europe to look for new resources under our own feet or exploit old resources where they were perhaps mined inefficiently. But again, this raises the issue of indigenous mineral production, which is something society has to make a decision on. So just sort of raising the point that within Europe we do have potentially the answer to some of the metal supply problems if we're willing to tackle these. I think at that I'll pass on to Friedrich. Please do.
Yes, Friedrich, go ahead, please.
Thank you very much, Nick. Thank you very much, Richard. Yeah, I'm looking at the whole situation of mineral supply more on a long-term view. When we talk about criticality is always a matter of the present situation, what the technology is, what the political situation is, which changes quickly or can change quickly. A good example is chromium, for when the Club of Rome report came out in 1972. At that time, there was also, everybody was concerned about metals. Lots of criticality studies were done, and on top was always chromium. If you look today at the studies, chromium is hardly mentioned, so the situation has totally changed. And this will be also for other metals to come. We have one resource, which is our brain, the man, for me, unlimited resource of creativity, and so I think the problem is solved. We have a basic problem concerning the production of raw materials, and this is you have to have access to land, you have to have water, you have to have energy, and you have to have people. Now, access to land is very connected with people, because if they restrict your access to land, then you have a big problem. It's a people problem. And if you, if you really analyze it, energy problem can be solved, water problem can be solved, but what I think is really problematic is the people problem, that the miner has to have a social license to mine. If you mine, as what you do, even if you reclaim it perfectly, you have to make a hole in the ground. You can't do it without it. And this becomes more and more unacceptable socially. And I think that's a very, very basic problem for our future mineral supply. Thank you.
Okay, thank you, Fred. So just to reiterate some of the main points that came up, one notion which we find a lot, which if we look through the literature, is the notion of peak copper, like peak oil, the idea that eventually society will exhaust available supplies of these metals. This is one thing we can discuss. More specifically is the question of supplies of metals for Europe. In the Eramin network of Olivier, a number of tactics are discussed. It's clear that we must improve the level of recycling of metals. It's clear we must look for substitution of some metals. But it's also very clear that in the present world, with the increasing demand in China and India, new sources of primary metals must be found. Are they going to be found in Europe? How is Europe going to get their supply? And this leads to this very specific question is, to what extent can the supply of metals required for European industry be satisfied by external demands, by importation, or should we consider increasing the amount of mining that is done within Europe? So within that introduction, I'll ask you for questions for all the three speakers.
I'm Jonathan Tyrone with Bloomberg News. A couple of questions. Could you identify geologically where some of the more promising areas in Europe are for some of these 14 elements that have been identified? Along with that, and going towards the NIMBY problem, the not in my backyard problem, there's this company Linus that had to ask the International Atomic Energy Agency to broker its development of a rare earth metal installation in Malaysia because of the fear of radioactive contamination from the processing of the metals. Could you speak a little bit to the actual state of knowledge about how these are processed once they're out of the ground and what kind of risks exist?
Mm-hmm. Okay, well, Richard, probably you're best to answer the first question.
Yeah, certainly. I mean, for example, the example I mentioned about cobalt, the nickel's currently being mined in Greece and through across in the former Yugoslavia and through to Albania, and the metallurgical technique they've been choosing serves to leave the cobalt in the slag, in the waste, and their implementation of a new technology can increase the recovery. And because you're recovering cobalt, you could perhaps make some of the deposits that were formerly closed after the collapse of Yugoslavia, for example, communist era, when it was mined, they could then be reinstated and increasing the production. We've got new exploration going on very successfully, particularly in the Nordic countries, places like Finland, which have, you might say, a pro-mining attitude, but should we say they're supportive of industry, whatever it is, and mining is one of those. And there have been some very exciting new discoveries there of nickel, cobalt, platinum group metals there. So that's one example where, when you have the license to work, you can find new deposits. And there are two examples in Europe where you could cite that there are world-class deposits to be found. Maybe on the, I don't know about the recovery side, the license to mine. Maybe Fred's got some.
Fred, I think you'd be best to answer.
Yeah, I'm not an expert about the problem of Linus in Mid-Mount Welt. The deposit is in Australia, and they want to process this in Malaysia. I can only give you some facts. The fact is that the lanthanides, the rare earth elements, are very close to the actinides in the periodic table. So very often you have radioactive materials connected with rare earths. That's true, mineralogically true. So there were, for example, if you have wave action and you have heavy minerals, there is a so-called mineral monazite in it. Monazite has also rare earth and it is also radioactive. Formerly it has been used for rare earth production, but because of this radioactivity problem, it is not used anymore. So what's the fact is, for the people who are concerned with radioactivity in Linus production plant in Malaysia, I don't know, I cannot comment on that. But I think the idea to get people in from here, the International Atomic Energy Organization, that's quite correct. I mean, these are the best people, and they are neutral. So whom in the world can you get best to give an opinion? And I think they are totally impartial. And if they have a radioactive problem, they will say. And I think I hope they are so convincing if there are no radioactive people that they can convince them. But this is one way to build up confidence, to have absolutely not neutral people.
Yeah, we had an interesting talk this morning about the different sources of rare earth elements, and what I learned was that a very important criterion in establishing the value of a deposit is whether or not it contains these radioactive elements, which are a waste product, which are difficult to get rid of. So this is the basis of the issue that you brought up. Another question?
My name is Antonio Sanchez with EFE, the Spanish news agency. What can the scientific community, what kind of answer can you do this respect? I mean, should we follow the way of try to find these resources in European soil with new technology, with new techniques, or finding these geological resources in places where until now we don't know that they are waiting for us? Or the solution is, I don't know, because if we say that importing is not anymore an option, I don't see any other way than finding these resources in our own. So it's a social problem more than a geological problem.
Yeah. So, Olivier, you?
Yeah. Well, I think there is no unique solution. What is sure is that over the last 15 years, there was a huge increase in the demand of raw materials, and there is no reason that this will change in the forthcoming years. So I think we will all agree saying that we have to improve our resource management, and raw materials are part of these resources. What we will have to do is to better extract, better use and reuse, and better recycle. This is the only way to solve the problem. And this is where research and innovation, industrial innovation, can really play a role and of pivotal importance here. Well, this is in this context, for instance, this is the role of one of the objectives of ERM, as I said before, to foster this research and innovation. In the field of primary resources, in the field of recycling, in the field of substitution of scarce element by less scarce element with the same functionality and the same properties. The environmental issues have to be taken into account also. There are other problems which have to be solved, like regulatory framework. It's not only a problem of resource in Europe, it's the problem of accessibility of this resource. To answer also your question, so Europe is well endowed with natural resources. This is not the problem. The problem is first to the social acceptance. So the public opinion about mining, in particular, is not that good at the moment. Although much progress has been made over the last years, and there are nowadays possibilities to have an environmentally friendlier mine than before. There are also alternative solutions to extract metals, like bioleaching, for instance, or using the bacteria to extract metal with a minimum environmental footprint. So there is a bunch of things to work on, and I think it's the combination of all these approaches, considering the entire raw materials value chain, which will bring something in the future. So.
Please. Yeah.
You have here in Austria a wonderful example how this can be done. There is a tungsten mine in Mittersee, close to at the lake, Sellamsee. This mine was discovered by a brilliant idea of a professor in Munich, Professor Maucher. He had the idea concerning horizon, which is favorable for tungsten. Then this tungsten deposit was brought into production, and this fits perfectly into the landscape. It's a perfect example how in agreement, it's a Hohentown area, how in agreement you can mine, and with nature you can mine. A perfect example, and I don't see why it can't be repeated in Europe.
Yeah.
Can I just say something as well? I think from what you're saying also, there needs to be an engagement of through the life cycle of the use of these metals. And I think that's perhaps we've fallen down a little bit in Europe. We're big users of these metals. And it's only now when industry is beginning to realise that there may be some supply issues that they want to understand where their metal's coming from. I mean, most people understand now how in Europe where their food comes from, and there's a lot of concern about where your food is being sourced, how far it comes, and all those issues associated with the growing, the transportation, the using, and then the disposal of the waste after you've eaten your food. And the same probably should apply to minerals. We should be doing the same thing, understanding the life cycle of the metals so that we can see the areas where we can get recycling into the system, and that people understand. We need to start to educate people about their mobile phone, how many metals they have in there. So it's all very well complaining about where these metals are coming from. When you're speaking to somebody on a mobile phone, they should know where those metals are from. So everybody should be, should have the information to be able to make those decisions, rather like we do for the food now. I think most of the public understand those issues, and probably we need to instigate something like that for metals in Europe particularly, because although we don't mine much, we use a lot. If you look at the German economy, it's underpinned by natural resources, raw materials. Not all of it can be recycled, some can, and hopefully more will be. But those metals, particularly with changing industries, the scientists based in Europe can help respond to, where will those metals come from? Can we source them indigenously? If not, can we secure them somewhere else that's going to be beneficial to Europe and beneficial to people who supply those metals to us? So it is a mixed thing. There's not just one simple answer. But I think if we engage from the top to the bottom of the supply chain, it's the mind expertise which Fred said that Europe excels at, that where we can really put a lot into this mineral cycle.
Thank you, Richard.
How about this situation? I mean, how long do we have to find a solution before the situation gets really critical? How long can we afford to import this expensive material,
Okay, well, maybe this is an important question, because you have to distinguish between long-term and short-term crises, potential deficits, and maybe somebody can make the distinction between the potential shortages which will happen in the short term, in the period of a couple of years, and on a longer term basis. Fred, maybe you're the best to do that.
Okay. You have basically to distinguish between two main natural resources. One is energy, based on fossil energy or nuclear energy, and certainly one day it's not so close, but one day these fossil energies are gone. So we have to go find the way for renewable energy anyway. Otherwise, the whole society runs against the wall. But concerning non-energy minerals, we are not wasting them, or we are, let's say, destroying them. Atoms don't get lost. We transferred from the primary sphere, from the geosphere, into the technosphere. And we have to learn to get them out of the technosphere again, recycling everything to make it a closed cycle. And the first thing, scrap is much more advantageous to use it as copper, as primary copper, because the energy balance is far positive. You need only 30% of the energy for copper if you have secondary copper. You need only 5% of the energy if you have aluminium cans to make copper out of it instead of bauxite. So, but there are other materials which are very much dispersed, where the energy requirement is much higher, and there are other things which so far technology to recycle it has not been really developed. This, for example, this is a good example for that. But the more we use and the more we transfer from the geosphere and the technosphere, the higher is the chance that we actually can live from the technosphere. So for me, there is no end. We are brilliant enough to find solutions to get it back out of the technosphere. You can say that, for example, when I started my career and we worked on this, I was working with a company who developed this mineral deposit, recycling was less than 10% of tungsten. Today it is 30%. So technology improves. And I'm optimistic that man will not become stupid and finds a way to solve it. And the guiding principle is always price. You know, if the price is high, then you can also recycle lower grade scrap. And and then some people say, okay, prices must go up. I'm not so sure. Prices for all raw materials over the last 100 years, if you get inflation out and calculate it, they have been horizontal. There was no price increase. And I'm optimistic that will also be achieved in future. But, I mean, I can't approve it. That's my personal optimism.
Okay, thank you, Fred. Another question?
Hi, Liz Gallagher from Environmental Research Web. Continuing in the recycling vein, can you comment on which materials are relatively easy to develop recycling technology and whether there are any where it's just not possible?
Maybe Olivier, you could answer that.
Well, yeah, it's a difficult question. The main challenges, I think, right now concern the rare earth elements, which are really difficult to recycle. This is a technological problem, of course, but it also comes from the very high dilution of these elements in the electronic devices, for instance, that could be recycled. So there is room for technological progress here, but we have to work on it.
Richard, maybe you can make a comment about the cycle of the lifetime of materials within infrastructure, which has a major effect on the recycling possibilities.
Yeah, I think one thing we must bear in mind is that quite a number of bulk commodities, if they're put into infrastructural projects, then they're not readily available to be recycled. I mean, a good example would be, say, copper. If we have a developing economy like China and India, you're putting in copper wiring, say, into a home in a village that gets electricity. That copper wire is put in there. It's an infrastructure, if you like. It's a lost bit of copper, and for 25 years, that's going to be in someone's house, letting electricity go around there into their light bulbs. You're not going to then be able to recycle that. So there's a long lead time of putting things into infrastructure before we can develop recycling. And for example, for copper, we're in that stage where you're building economies, and an economy like, say, India might use only 0.5 kilogram of copper per person per year, whereas somewhere like the US would be over 10, So if you expect someone in India to want a lifestyle like that in the US, then they're going to go to that level. So there's definitely a certain amount of the metal in that case that is not going to be available for recycling for tens of years.
Fred, could you just give a quick grouping of metals that are easy to recycle and can be recycled effectively, and those that are more difficult?
Yeah, sure. Well, the easiest thing to recycle is batteries, lead. Most of the lead goes into batteries, and batteries have a lifetime of 5 to 7 years. You all know it. You all drive a car, and it can be easily recycled. And if you look at the statistics, I did this for Germany. Practically all lead which is used for batteries comes from the recycling. So this is practically a closed loop. There are certain things going into chemicals. These are lost, and this will be very difficult to recycle them. Then the next one is copper. So the recycling rate for lead in Germany is 65% or 60%. So then comes copper. It is also more than 50%. Okay, first I have to explain what actually the recycling rate is, what the statistics is. The statistics is not what you recycle, what the scrap which is available. So, for example, if you read the statistics about glass recycling in Austria or in Germany, it is the amount of glass which is in the economy collected and is recycled. By metals, it's totally different. The metal recycling quota is the percentage of the metal used in 1 year which comes from recycling. So it has a long lifetime behind it. So, as I said, short lifetime for lead, it is 60-65%. Next in Germany is copper. I think it is also 55%. And then comes aluminium. And then it becomes difficult. Zinc is used in coating of protection against rust from steel, is dispersed. Recycling rates are lower, I think around 30%. Well, and then comes all these other minor metals, and then the recycling rate go very down. Well, for molybdenum and chromium, I think the recycling rates are in the range between 20 and 30%, or even lower.
And is this a final situation? Can they be improved, or are there strategic technical reasons why the recycling rate will always stay low?
No. I think, as I said, the example of tungsten I gave, this can be improved. Yeah. Okay. And one can also improve downgrading. I just heard a paper. Nick was also there in the early on in the conference. There was somebody from Chambéry who gave an example about eco-design and recycling. And he gave a wonderful example. You have a, what's that name, cooler, what you need in a car to cool the car.
Fan. And air conditioning?
No, not air conditioning.
No, ventilator?
What you use for a ventilator for heat exchange. This is made out of aluminium. And the connection is made out of copper. So when you don't separate this before, then the copper gets into aluminium. And because aluminium is much more noble, copper is lost. So you have a deterioration of aluminium and you have a loss of copper. So all these things can be improved. There are many, many ways of improving things of recycling.
But from the design stage, so the main point is that there has to be, the manufacturers must take steps to construct whatever they do in such a way that recycling, separation of minerals is more efficient.
So there are many, many screws which can be turned to improve recycling.
I think also in at the mining stage, we can do things to improve recovery of trace metals from what was previously thought to be waste. I mean, we have waste dumps that could be recycled, but also, one thing that would be worth trying to move towards is to create as little waste from mining as you can, so that all elements that might be there could be practically recovered. This is where this solution mining, the bio-leaching that Olivier talked about, is a case in point, where once you get everything into solution, you can then, through various ion exchange technologies, recover almost the periodic table of metals, perhaps. So we can look to those kind of technologies to improve the mining operations we have. So although it's not technically recycling, it's waste elimination, if you like, and optimizing extraction of commodities, so that you don't just mine a deposit for one commodity and throw the other things away. You somehow make it the other elements that are in that deposit available to be recovered.
Other questions?
Have you seen any evidence that the absence of some rare earth metals has prevented technological innovation, for example, in something like deploying superconductivity? I think some of the rare earth metals, that obviously would feed into more energy efficiency, but without the proper price signals, then you're not going to be able to bring those kinds of technological innovations onto the market. And along with that, just briefly, if anybody is prepared to say, isn't this a clear market failure, in fact, that there hasn't been any appropriate price signals for developing these natural resources for a long time?
Well, again, Fred, I think you're best to answer that.
Well, I would not know any example that the price of natural resources has prohibited everything. It is governed by price. Let's say the example of dysprosium. Dysprosium, you have for windmills and for magnets, you need neodymium.
These are two rare earth elements. Is a heavy,
But the neodymium loses its property of magnetism around 80 degrees. So much higher, you have to have dysprosium. The dysprosium price exploded from 2003 to today. The dysprosium price increased by 10,000%. But I don't know that anything has been stopped from developing. Windmills are progressing, and people become creative to find new solutions. For example, at this conference I just mentioned, there was a guy from from the Ford company, and he said, well, at that time when we designed our car, nobody thought about criticality where the motor for starting was. Well, now we found a place where you could actually didn't need so much dysprosium at all. You could put it in another place, and then we needed only 1/3 of the dysprosium which we needed before. So people think about it, but that really thing has been stopped. I don't know, because it goes through first the experimental stage, and in the experimental stage prices didn't play a role. I mean, if you pay 2,500 euros, dollars, I think prices on dollars per kilogram, and you pay 10,000, no research is stopped because of that price.
Yeah.
So I don't see any example.
There are other examples. Rhenium, for instance. Rhenium cost $300, 1 kilo rhenium, $300 in '96, and now it's about the same, about $10,000. So, but there is no shortage in rhenium anyway. So because people find solutions to either substitute the element, or there is investment in the exploration and extraction of rhenium, and people learn to use less material and so on. So
I think, though, the failure would come if you failed to support the scientists who came up with those solutions. That's so in a way what you're saying is correct. There has been no failure, and so that's, and the reason there has been no failure, someone solved it somewhere, but it would be good if that kind of problem was solved by the technology companies in Europe for our industry benefit, rather than perhaps somebody else making those discoveries because of those pressures. So I think we have been successful in staving off any complete shortages, but I think the warning bells are there, are prescience really for something that could happen, and it's maybe more of a warning than saying, yes, we've got a failure. Thankfully, we haven't got to that stage, I think.
So if I could just summarize. Taking the case of dysprosium, this heavy rare earth element, the price increased dramatically, and industry responded quite quickly in two ways. As Fred said, by finding ways to use magnets where heat resistance was not necessary, meaning that less dysprosium had to be used. And also the major car companies now are going back to the idea, to asking the question, do they need permanent magnets which require dysprosium, or can they use electromagnets? So in that sense, the market is very sensible to price signals. Other questions?
Are you aware of how are other economic powers facing this problem, if they have this dependence problem? I don't know if the United States or in Russia or in Brazil, the dependence on raw material is so high as in the European Union, if they are making steps in order to solve it.
Who would like to answer that? Olivier?
Well, you mean if these developing countries take care of their resources, or?
Yeah, especially in the United States, for instance. I don't know if they have their own resources, so they are not so dependent on raw materials as the European Union countries are.
It depends on the raw materials you are talking about. Mm-hmm. So, of course, emerging countries need a lot of base metal. And high-tech sectors needs more specific raw materials, so it's not exactly the same issues. Japan and the US and Europe is dependent, for instance, on the import of rare earth elements. We all know that. We are less dependent on the import of copper or zinc, maybe, also in Europe. So the global share of mining of the European Union is quite low. It's about 3%, so we can increase that. It's not the same situation in other parts of the world. So I think that there is really a difference between developing countries, the need from developing countries, and the need from developed countries.
Yeah, but maybe we can just go a little bit further into that question, because you mentioned three types of countries. Brazil, which is a big producer of metals and not so much a consumer. Korea and Japan, which are consuming countries, rather like Europe. And I think the policies adopted in Korea and Japan are rather different, have been rather different from that of Europe. But does anyone like to comment about that, Fred or Richard?
No. I mean, the policy of, especially of Japan and also Korea, was what the European countries companies had totally forgotten. I mean, they used raw materials like you go in the supermarket and buy sugar. You are not thinking, oh, where comes the sugar from? And so they also bought these raw materials like that. The Japanese were always totally different. They always encouraged companies to reintegrate them, the small shares, into mining companies, so they had a source. And the Chinese did this very, very intensively. Chinese shares in world mining companies are continuously increasing. And concerning the US, perhaps one should briefly say, the US have a special situation concerning their military. They have a stockpile. There they use the stockpile and stock very, very critical materials. But this is purely for the military, for nothing else. Otherwise, the US are a classical market economy system. Raw material supply is a matter of the companies.
Mm-hmm. Toyota is getting into partnerships with mining companies in Africa. European car makers do not seem to be doing that, and it's not very clear why.
No, I mean, we can see the same with China. I think Fred was mentioning there, a lot of the Western major mining companies have large Chinese shareholdings in those companies. So they're doing the other thing that I was saying, is not only looking at indigenous supplies, but securing overseas supplies. And certainly China's been extremely effective at that. I mean, look at cobalt's a great example. They probably control, nearly 3/4 of the cobalt market, because they process and refine a lot of what comes out of the DRC in Congo. And they've done the same with a number of metals that they see as being strategic to their industries, that the Chinese companies will go and either secure something overseas if it's not produced indigenously. And likewise, they put a lot of money into research and development. We've seen huge numbers of Chinese scientists coming across to get trained for the purposes of beefing up their own research efforts. So they're aware that science is the way forward to get them out of these kind of areas. So definitely countries like that have developed in a two-pronged way, securing the supplies, but then also putting a scientific infrastructure in place to then presumably face any of these problems when overseas supplies dry up. They can then become innovative in the way they approach the metal supply.
Mm-hmm. So yeah, Korea and Japan had been doing that earlier. Now Europe is starting to do that, thanks to the type of network that Olivier talked about, ERAMIN and so on. Other questions? No other questions? No? Well,
if not, we'll finish here. Thank you very much. That was very good. Thank you all for coming. This was the last EGU press conference. I hope to see you again next year. Thank you.
Thank you.
Thank you.